Okay, thank you, Simon. Simon, just to let you know, I can't see any questions or chat at the moment, so if there's anything, feel free to jump in.
That's okay.
So yeah, my name's Tom. I'm from the University of Bristol, and we spent the last few years flying drones in and around and over volcanoes. So you can see a picture on the right-hand side there of Volcan de Fuego in Guatemala. This picture was taken from one of our drones in March 2019. The purpose of this particular flight was to take ash samples from that plume from the volcanoes that erupted. My email address is there if anybody wants to contact me afterwards. So the background to this, I'm going to talk a little bit about myself and how I came to end up in flying drones. My particular background is flight dynamics and control system design for aircraft, both piloted and unmanned or uninhabited vehicles or drones. And then I'm going to talk a little bit about Fuego volcano, which is the main focus of this talk. And then at the end, I'm going to show you some video from Manam volcano in Papua New Guinea, which is another one that we've studied. And on the right-hand side, you can see the vent from Manam volcano as we're about to pass over it. And in this case, we're doing some gas measurements on board real time with the vehicle that was flying over the vent. I'm going to keep my talk also relatively non-technical, so dealing with a lot of the lessons learned and the things that we've done practically in the field. And that really stems from the fact that I like flying a multiple number of vehicles. You can see top left is taking one of my PhD students for a ride in a microlight. So I have a microlight license. We send all our students gliding as well up at the Bristol and Gloucester Gliding Club. And I'm also a founder of Perceptual Robotics, which is using robotics for inspection of wind turbines. You can see on the right-hand side. One of the great things about working at the university is the people that you meet and you interact with. And on the left-hand side there, I've got Professor Jim Freer, who I happen to be sat next to in a course I was doing, an internal course here at the University of Bristol. And he happened to ask me, do you know where Ascension Island is? And I said, I have absolutely no idea. A couple of years later, Professor Matt Watson, by the way, Jim Freer is hydrology is his area of expertise. Professor Matt Watson, who is into volcanology, Professor of volcanology, do you know where Fuego is? He asked me the question a couple of years later. And then Dr. Emma Liu asked me, do you know where Manam is on the right-hand side there? My answer to all three was no, but I could point them out on a map now because I've visited all three, plus other places during the course of this work. So the first lesson learned is talk to your colleagues, especially if you're interested in cross-disciplinary work, because they can often set you as engineers really interesting challenges. And some of the most interesting work that I've ever done has been inspired or based around problems or challenges that other people have presented. So yeah, a lot of credit to those three people and my thanks to them all. So I thought I'd start off with the lessons learned. So when I get cut off towards the end of this talk, at least I'll have covered these. So I put these down, and these are sort of the ones that spring to mind most often. A lot of them chime with things that previous presentations today have talked about. In particular, a lot of the ones that Tom Scott has talked about this morning. And this is in no particular order, except perhaps the first one, manage the risks and safety is paramount. You know, top of all the overseas, and I'm talking specifically about overseas field trials here, is that safety is paramount, because if you get that wrong at any point, not only do you put people at risk, but you also put at risk the projects that you're doing. So everything that we do has safety and managing the risk at the top of it. Do your homework, collaborate closely with the local people and institutions. So wherever we go, we always speak with people locally and work with the institutions, because you're guests as you visit. And actually some of the most enjoyable parts of the overseas field trips is when you work with local people, learning from them and helping to support their learning in the areas that perhaps you have expertise in. And places, for example, in Guatemala, we've got Insabume, who we work closely with. They're the volcanology group out there, a local government volcanology group, and they've been absolutely fantastic in the support of what we're doing, and it's great working with them and developing the systems and the methods that we use really in partnership with them as well. And any time spent working with them, setting up links has never been wasted in my experience. Don't ever count on just one deployment. The best results come from multiple visits. Go out there several times. I've visited Guatemala probably 5 or 6 times now, and most places that I've been and flown drones, we've been there for 2 or 3 visits at least. Because the first time, you never get everything right, and you can always improve on it. The other thing that I tend to do is include what we call a recce trip as well. So the reason to do this is to go and have a look at the challenge before you get there. So you can look at things in videos and on Google Earth and talk to people remotely, but there's nothing like actually standing on the spot, looking at what you actually need to do. Where you perhaps have experience in the robotics that you're deploying, the people locally don't know the challenges and the boundaries and what you need in terms of support locally. The other reason for going on a recce trip where you're not actually expecting to fly or deploy anything is that you're under no pressure to do so, which actually pressure can lead to you making choices that perhaps aren't the best ones. So the best results I've got is when I've gone to have a look at a problem first and then gone back 2 or 3 times afterwards, each time ramping up what you're doing in terms of the complexity of the deployment. Do the preparation and the paperwork before you go. Do your homework. So make sure you have the paperwork in hand, as Tom was saying earlier, and make sure you're prepared as much as you possibly can. Deploying it in the field is nowhere near as easy as deploying it in your field at home, where you're flight testing or ground testing. And it's typically an order of magnitude more difficult when you're doing it in the field. So the more preparation you can do, the better. The more paperwork you can do, the better before you get there, because it'll ease things as you go through. If you're traveling internationally, pack carefully and lightly. We talked a lot about batteries earlier this morning as well. Having had some interesting experiences, my preference now is to take absolutely everything with you when you go on the aircraft. Now, most of the aircraft we fly are relatively small, and depending on the airline, and it actually, you can contact the technology people in the airlines themselves, which we've done in several cases. And in some cases, you can break down batteries and you can carry them on the airline in smaller packages, and then you fly them in larger sets. If you need to send them by ground, then you do so. But if you can avoid doing that, that would be my recommendation. But look at the rules and regulations carefully, talk to the airlines before you turn up, and make sure that you have a plan for how you're going to get everything out there. Checklists, both pre-flight checklists, but also pre-departure checklists before you go overseas, work really, really well. One of the great things about doing this is you get to work as a team. And so the team sizes that we have can be anything between 3 or 4 people up to, I think the largest team we've had so far is 12. Managing a team larger than sort of 6 or 8 people can become a little bit more difficult. But what you're looking for is complementary skill sets. So you're looking for people that can complement each other in the field and have the relevant experience to do that. And you might have, if you're setting up a team, a mixture of experience levels. So you might have somebody who's never been out there before. You might have people who've been traveling a lot. And above all, you need people who can cover each other and support each other in the technical skill sets. No one person has all the skills you need. And so you need to look for a range of people. And the best trips that I have been on has been with sets of people who get on extremely well, who are extremely good technically, but have complementary skills that they can offer. So the team is really key to everything, and selecting that and setting it up carefully before you go it will help immeasurably to get good results at the end. Something else that Scott said, have a clear test plan, but be prepared for it to change. Absolutely. But it's good to have an idea of what you're trying to do, have a clear test plan set out, but be prepared to be flexible depending on what happens on the ground. Don't invite cameras early on or on early trips. Cameras being the media, perhaps being Discovery Channel, perhaps being the BBC. There's a range of different people. They can be interested in these kind of deployments because it's robotics, it's interesting environments, it's people in the field, but they put pressure on a trip. And we've been in the position before where we've had cameras on us and it hasn't been going so well, and that can be really difficult for the people involved. And then the last one, brush up on your geography. So at least when you say you're ready to go somewhere, you know where you're actually going. But that's basically a list of points that has helped me in the past and will help me in the future. So when I found out where Ascension Island was, I then traveled there with, there were 4 of us who traveled there. We went there 3 times. We did that recce trip, which I said to go and have a look at the problem first. And then we went out there for 2 trips afterwards to fly drones. These were the ones that we flew. We built them in-house. They're from off-the-shelf parts, but we set them up ourselves to solve a particular problem. In this case, it was to fly to about 7,500 feet above ground level. And underneath, you'll see a white box here. And what we were doing is we were flying them up to that level, and then we were pumping up what we call Tedler bags. And then we bring those back down with the samples of the air from altitude. And then these are being brought back to the UK for analysis. So the challenge was to get drones up there and down again. In the end, we went for multi-rotor drones. And we did around about 100 flights and got probably around about 100 to 150 samples in total. Some of the flights we had 2 samples. The idea behind this was to capture air that was coming from Africa across the Atlantic and also from South America across the Atlantic, depending on the wind direction at the time, and to take samples from above the inversion layer. And drones proved to be a great way of doing this. And there is a publication there if anybody's interested to find out more about it. So this is Jim Freer, who introduced me to that. He then introduced me to Matt Watson, and Matt Watson said, do you know where Guatemala is? And I said, no, and then he told me all about this volcano, and then he took me to this spot here, and you can see the picture on the right-hand side, and said to me, well, what we'd like to do is we'd like to sample that ash plume that is coming out of the top of the volcano. So the challenges involved with this is that we would need to fly BV loss, which is beyond visual line of sight. So we need to fly the vehicles without being able to actually see them. We need to fly them up to about the ceiling, maximum ceiling we've reached is 18,000 feet above sea level, and operated it. And excuse me for mixing my meters and feet here, but we've flown them up to about 12 kilometers from where we took off. In terms of the field challenges, you can see the kind of vegetation of where we are around the volcano. And I've come to learn that volcanoes don't include a lot of flat land around them, and certainly not flat land with runways on them. So actually just getting the vehicles off the ground and back on the ground safely has been a bit of a challenge. So we said yes. And just to give you an idea of the geography here, we've got the observatory, which is in Savume, who we're working with. And this is where we are launching our fixed wing vehicles from, climbing up towards the top of the volcano and looking to intercept the ash plumes that are coming out the top of the volcano here, roughly moving right to left in your image with the wind. We can fly multi-rotors across if we climb up a Catenango, and that's about 3 kilometers to send them across from here. But getting up here and operating from the top of a Catenango is actually really quite difficult. And certainly not something we'd want to do for a prolonged period of time with a fixed wing. So fixed wing came from the observatory, multi-rotors we took across from Catenango. The funding for this is coming from a program grant. It's a 5-year program grant funded by EPSRC, working with a number of different universities. We've got Cranfield, Southampton, Manchester, Imperial College, and ourselves here at Bristol. And I would like to take the opportunity here to thank everybody in country, both in Guatemala and everywhere else that we've worked, for their support. So in Savume and DJAC are responsible for the aviation permissions that we need for operation in Guatemala. And then also I've named a few people that from Bristol that we worked with on the way there. And you know, another takeaway is that taking robots into the field can be highly challenging, but it can be highly enjoyable as well. So some of the best work, most enjoyable work that I've done here has been doing this kind of thing. So as part of Cascade, I said that I would sample a volcano plume, which is what we did. And so we looked up at Fuego, and you can see Fuego on the right-hand side there. And the nice thing about Fuego is it erupts around about every 10 to 20 minutes with small eruptions, releasing small amounts of ash. And the idea is to target these ash plumes with our vehicles. So you can see a couple of the fixed wing vehicles that we're using here on the left-hand side. These are just off-the-shelf airframes, and then we put in our own avionics, flight controllers, companion computers, and also sensors that we're looking to detect the plumes themselves. And you can see the observatory here with the ground station set up. And I'm going to be returning to that in a couple of minutes. So there's the challenge. Those are the vehicles, and here's some of the people during one of the flights. Now, drones are highly capable vehicles now. If you look at this 3D model here, this is a model of Fuego volcano, which was put together from photographs taken from forward-looking cameras and downward-facing cameras, but two of them on a single 40-minute flight over the terrain surrounding the crater itself. So in terms of working in partnership with the local people, Fuego itself is surrounded by about 100,000 people based in different towns and villages, and they live within the vicinity of Fuego. And the more information that we can help to provide, and the more that we can help in Savume in their journey in terms of using drones, the better. So this gives you an idea of the kind of thing that can be very helpful for in Savume when they're looking at monitoring the volcano. This model coming from a single 40-minute fixed wing flight. If we can get to the point where in Savume can carry these out on a regular time period, then that can help them to monitor the volcano and help inform the local populations that live around it. So to our challenge of actually taking samples from within the ash plume itself, Alex McConville, one of the PhD students here at Bristol, designed this ash collector. And the idea behind this is we've got two independent arms that can actually fold up and fold down again. And so they're protected on takeoff and landing. And then when we're ready and we're flying through the plume, we can deploy these ash collectors. They've got sticky stubs, military grade sticky stubs that stick in the front of them. And we've got an airflow disruptor in front of them, which disrupts the air, slows them, tends to slow it down and help with actually collecting the ash on these stubs. So we built these into the top of the vehicle, and then we started flying them. So we found you find actually just small changes sometimes can really help. So we actually moved, originally when we were flying, we had a party that was deploying the drones, and we had another party that was actually working with them when they're in flight. And we actually moved the party who were the ground control station crew, we moved them outside, and having closer to the launch and recovery site actually helped with communications. So you make minor changes all the time as you go through the flights and you go through the deployments in order to improve what you're doing. These vehicles here, taking off, we could spend about 20 minutes at the top, near the top of the crater with the normal lithium polymer batteries we're flying with. When we moved to lithium ion batteries, cylindrical cell batteries, we found we could extend this significantly to about 40 minutes near the top. When you take off, by the way, you have no idea when the volcano is going to erupt next, so you need to be able to react to what the volcano is doing during the flight. This is just to show you one of the takeoffs that we had. This is a barranca looking up towards the volcano. See Ben there launching fixed wing taking off. And what we did was, again, we upgraded the vehicles over 2 or 3 deployments. We put better motors on them, better speed controllers on them, better batteries on them, and then you're flying them right at the limits of what they can do. So here's another takeoff. And Ben being quite pleased with the takeoff there. And we're flying the vehicles really at the limits of what they can do. And we do that because we've got experience in doing it, and we build on that experience over each flight and over each deployment. You can see here the photo I showed you earlier from March 2019. And the top of Fuego, we're actually based down the valley here, about 8 kilometers, and we're about a kilometer in front and about 1.5 kilometers away from the top of the volcano going off. So at this point, we're heading towards the volcano, and we're looking to intercept that ash plume. The other thing that's interesting is how you interact with the vehicles and the robotic systems themselves. At what level of autonomy do you want to do it? And depending on the model that you use, there might be 4 or 5 different levels. And we found the ability to go from relatively from pre-planned automatic flight to controlled flight through a pilot, but in a way where the motion of the aircraft is constrained, was actually very useful. So you can see on the left-hand side here, you can see the yellow and the blue flight, which is the pre-planned part of the flight. And then you can see the sort of pinky area is the bit where Ben, the PhD student who was launching it earlier, is flying it in a fly-by-wire mode, where the flight of the aircraft is protected, but he is steering it effectively around the sky and looking for these plumes and then flying it through the plume. And you can see here we've caught some ash on one of the stubs. So being able to move through the levels of autonomy, giving good situational awareness both to the ground control station, also to the pilot, really does improve the success of the missions. As you fly through a plume, can you detect it automatically? Because the long-term vision of this is to still have a pilot you can step in when we want to, but we want to do the whole thing fully automatically. So we want to visually detect the plume, fly towards it. When we fly through it, you'll see on the left-hand side, we've got changes in temperature and humidity. These are characteristic here in the middle, in the center with flying through the plume. You can also see on the right-hand side that there is a change in the pitch attitude of the aircraft as it flies through the plume. There's also a change in the throttle response as well, as the flight control system accounts for the fact that it's rising air. So we've actually put together an algorithm which will automatically detect whether you're in the plume or not. We want to link that with the vision algorithm to detect the plume, and then we can automate even more of the flight whilst retaining the ability to take manual control if we want to. So here's one of the early plumes that we flew through. And early on, again, you build up your experience of doing this. So you can see on this one, we're flying, we can see it. We could turn right and go straight towards the center of it, but we decided to go just to the left of it. You can see it's turbulent air as you go through. At this point, we would have opened the stubs, and we're picking up ash just from the edge of it. And then we turn left to bank away from the volcano and out into the air. And then if you continued straight on right now, at that point, you would have headed back towards where we were. But at this point, Ben's coming back through the plume again and taking another sample. So another lesson to take away from this, in particular if you're flying drones, is you might have an hour in the air with this particular type of vehicle. And really close communications between the ground control station, between the pilot, if you have a pilot who's going to take control during the mission, and knowledge of what the vehicle is doing, a good situational awareness for both the pilot and the ground control is absolutely critical. And one of the things we got to the point where we were so happy for doing this, I'm not sure this is the actual flight here that we did it on, but we did a flight at night. Visually, it's very difficult to see anything, but we had enough information that we knew where the aircraft was and what it was doing. And you can see here in this flight, we've got periods where we've got, oh, I've got a bit of feedback. There we go. Thanks, Tim. So you can see the automatic flight here in yellow, and you can see the manual flight here that Ben's doing. And having this ability to move between automatic and manual flight really helped what we were doing. Another takeaway is the more you do something, the better you get at it. So you can see there's a general increase over the different flights that we were doing. We were spending longer in the air. We were spending longer above the summit. And you can see here also, the blue dots, change in batteries significantly improved the amount of time we could spend above the summit. So if you're going to do something, don't plan to do it just once or twice. If you can, have multiple deployments and have multiple experiments during those deployments. I'm going to move forward in the interest of time a little bit with this one, but this was one of the largest plumes that we flew through. It's about 2,000 feet from bottom to top of the plume, and flying through it, again, taking samples, working also in conjunction with the ground control here, who were taking samples because this plume was so thick, it was actually falling out near where we were operating as well. And you can actually see some of the ash falling down that we were collecting at the time as we were flying through it. As we move forward, we're looking to automate the flights more than we were before. This slide here deals with, in this case, this vehicle as it took off from the observatory did not have a flight plan to get to the top. It had a companion computer, and we created the flight plan on the fly as we went up. And in the next deployment that we do there, we're looking at collecting ash both close to the vent and actually at a distance to the vent as well. So we're going to have algorithms on there that will plan the route through from start to finish. Okay, the next, I'm going to finish up relatively quickly now, but we've also looked at photogrammetry for plumes, and this is extracting information about plumes coming out of the top of the volcano, either from multiple drones or from multiple viewpoint angles, which has worked really well. We've also done quite a bit with in-plume gas measurements, and this is Kieran Wood from the University of Bristol and Emma Liu from UCL. And Emma then took us and led a team that came from all over the world to go and have a look at Manam volcano. This is Manam volcano in Papua New Guinea. We had a team from all over the world, and at Bristol here, we led on the flight safety part of it. So we collaborated with all these teams to make sure that we were safe, that we had the correct permissions. And when we were there on the day, we flew our drones carefully and safely. Just to give you an idea, this was our launch and landing point. This was the biggest area of flat land on Manam that we could find. So in terms of the fixed wing, this is where initially we launched and took off. And again, the people there were absolutely fantastic in order to work with, and both in their support of what we're doing, and to actually share our time with them when we're out there. Okay, I'm going to finish just with this, which is some video. This is in Chile, Federica volcano, that's the one in Guatemala. And just conclude that actually going on these trips has been absolutely fantastic fun, and we've done some really good science when we're out there. That's Ben Schenenberg, who's graduated with a PhD in the field deployment of UAVs. There's Rob Clark, another one of our PhD students. And yeah, if anybody wants to contact me, very happy to talk to you. And it's been great working with these people and deploying these drones in multiple places all over the world. So there you go, Simon. I'll stop there.
Thank you, Tom. Our host, Simon, is again having a few technical difficulties with Zoom, but it's all good. Does anyone have any questions for Tom? You can either come out of mute and quickly ask the question, type it in the chat, or type it in Slack. Any takers? All right. What I might do is, in the interest of time, I'll introduce the next speaker. Please do ask your questions on Slack, and Tom might be able to answer those. Oh, we do have a question on Zoom. Did you ever lose contact with the drone flying through the plume?
We've lost one. Unfortunately, we lost one in over Manam volcano in Papua New Guinea. The thing about the plume there was at the time when you're flying through it, it's highly energetic. There's an awful lot of energy in the plume, and we'd done a couple of flights that had gone very well, and then we flew into the plume, and the numbers that we got back from it showed that it out-accelerated a Formula One car vertically, and we're going to need a stronger drone in future. But that's the only one that we've lost to date. Yeah.
All right. Thanks for that, Tom.
Cool. Thank you for the opportunity presenting.
There are a few questions. I'll move them over to Slack so that they can be answered.